Dear viewers, this video is for you who wish to grasp the working principles, distinguishing features, and applications of Instrumentation Amplifier. Instrumentation Amplifier is used to acquire and amplify the difference between two voltage signals available from two different inputs. This signal is called differential signal. The differential signal is available from two output terminals of a bridge circuit. A sensor is placed in one arm of the bridge. When the sensing quantity changes, the resistance in the arm changes. As a result, the value of the differential output alters. In a different application, ECG electrodes connected to the chest of a patient generate another kind of differential voltage between two wires. Instrumentation amplifier acquires these different types of differential signals, amplify them, and present the output in a single-ended form. To understand the working principle, first we start our discussions on two types of signals. First type is the signal under interest, and the second type is the common mode signal. The signal of interest are applied to two input terminals A and B of the differential amplifier. The difference of signals are acquired, amplified, and presented at the output of the differential amplifier. A sample signal is shown here. The common mode signal, on the other hand, appears at both of the inputs of the differential amplifier. Here is a common mode signal appearing at both the inputs. When the common mode signal is superimposed on the signal of our interest, the output cannot reject the common mode signal completely. This is because the differential amplifier has two gains inherently present within it, one called differential gain AD, the other one called common mode gain ACM. They separately amplify differential signals and common mode signals respectively. The difference between two signals at two input terminals A and B is called differential signal. The average of the two signals at two terminals constitute common mode signal. Keeping in mind the nature of these two types of signals, each of the two signals at terminals A and B can be represented as a combination of the common mode signal and half of the differential signal. Ideally, the common mode gain is 0 so that common mode signal is completely rejected at output. A term called common mode rejection ratio, abbreviated as CMRR, is introduced to assess the relativeness of the two gains. The ratio of differential gain to common mode gain in the logarithmic scale is used to represent CMRR. For good rejection of the common mode signal, CMRR needs to be as high as possible. Here is the circuit of a typical differential amplifier. Any op-amp, maybe OP07 or anything else, can be used along with four resistors to construct a differential amplifier. The expression of output can be represented in terms of two ratios of resistors, one R4 by R3, another R2 by R1, connected to non-inverting and inverting terminals respectively. First, we consider that the resistors are perfectly matched, that is, R4 by R3 is equal to R2 by R1 expressed with some quantity K. The output as a result is the differential input VA minus VB times the gain R2 by R1. R2 by R1 serves as the differential gain AD here. The common mode gain ACM is evidently 0 in this case. But what happens when resistor pairs are not matched? To know the consequence of such mismatch, let us substitute the expressions of VA and VB in terms of VCM and VD into the expression of V0, the amplifier output. We arrive at the result where output voltage contains the two terms VCM and VD. Correspondingly, we get the expressions of two gains ACM and AD. We assume each of R1 and R3 has nominal values X and each of R2 and R4 has nominal values Y. Their actual value may deviate from their respective nominal values by some amount delta X and delta Y. We also assume that each of these deviations or tolerance of the resistors is within plus minus 1%. For the sake of easy explanation, we assume that the nominal values to be 1K and 10K respectively. Substituting the tolerances of values for the resistors in the expression of common mode gain ACM, we get the final expression. The value ACM comes out to be 0.0357 with all such chosen values of components. Similarly, the expression of differential gain is also found. This value is pretty high and is equal to 14.721 with all such chosen values of components. The resulting CMRR comes out to be 52 decibels. This value is high but not very high, so common mode signal is not completely rejected. The second problem of this arrangement is that input current at terminal B can flow between VB and V0 through R1 and R2. Similarly, input current at terminal A can flow between VA and ground through R3 and R4. Thus, the input resistance of the circuit is not as high as is expected. This problem of reduced input resistance can obviously be eliminated by connecting two buffer amplifiers at two input stages when input resistance is greatly enhanced. But the gain is not enhanced in this arrangement. The enhancement of gain is possible by connecting two more pairs of resistors, namely R5, R6 and R7, R8. These resistors impart the gain in first stage. The second stage gain is as usual with the resistors of differential amplifier. Now, the same circuit is drawn in a different way. The resistances R5 and R7 are connected common and then they are grounded. At this, the whole configuration remains exactly same. Here, R6 by R5 is made equal to R8 by R7, that is, they are matched to keep gain at every input amplifier terminal same. Now, if a common mode signal appears at A, it is also available at the intersecting node of R7 and R8. Similarly, its presence at B ensures that it is also available between R5 and R6. The VCMs therefore drive current through R5 and R7 towards ground. As a result, additional voltage drop takes place across the resistors R5, R6, R7, R8 due to common mode current. Thus, common mode signal creeps into the circuit towards the final output. To solve the problem of appearing common mode signal deep into the circuit, R5 and R7 are replaced by a single resistance RG and the grounding is removed. Also, the R5 and R6 are made equal. Thus, all the resistors are fabricated inside the IC except RG, which is left for external connection. The first advantage of such connection is that either side of RG carries the same common mode signal VCM. As a result, RG does not carry any current due to VCM. So, no common mode signal enter into stage 1. The second advantage is that overall gain of the amplifier is enhanced. R2 by R1 being fixed through monolithic fabrication provides constant gain. Along with the externally connected RG provides a variable gain. With progressively lower value of externally connected RG, the value of the corresponding gain increases. Thus, the entire configuration called Instrumentation Amplifier can impart high gain to the input signal. At this, even a small magnitude differential signal can be amplified to a large extent by an Instrumentation Amplifier, allowing extremely small common mode signal to pass through itself. Various types of instrumentation amplifier are available in the field of engineering. They can be a 3 op amp instrumentation amplifier, a 2 op-amp instrumentation amplifier, a current feedback instrumentation amplifier, fully differential instrumentation amplifier, high-speed instrumentation amplifier. There are a lot of advantages of instrumentation amplifier. First, a single resistor connected externally to the instrumentation amplifier IC is used for gain selection. Second, the provision of two-stage gain makes it suitable for introducing high value of gain. Third, it has high CMRR. 4. Input impedance is very high, hence it does not load the system connected to its input. Fifth, output impedance is very low, hence it is not loaded easily by a system connected to its output side. Sixth, it has differential input which is suitable for acquiring signals from a sensor-based circuit. The single-ended output is suitable for its connection to the port pin of a processor or a microcontroller. Instrumentation amplifier finds wide use in acquisition of sensor signal. When the circuits like Wheatstone bridge etc. contain sensor and generate differential signal with low amplitude, instrumentation amplifier can be applied there. In circuits for medical instrumentation, where the ECG, heart rate monitor etc. generate small and differential signals, instrumentation amplifier is the automatic choice. Low amplitude audio signal is also acquired by instrumentation amplifier. Instrumentation amplifier can also be used in the area of current sensing. There are several manufacturers who construct instrumentation amplifier ICs. Analog devices produce AD521, AD524, AD620, AD624. A sample connection diagram of AD521 is shown in figure. It is evident that the external resistor is used for gain selection. AD620 is relatively simple in connection, but the purpose of external resistor RG is same. There are other companies like National Semiconductor, Texas Instruments, Linear Technology, Maxim Integrated who produce ICs of instrumentation amplifier. The connection diagram of INA 128 make of Texas Instrument is shown. Last but not the least, developer can prepare their own instrumentation amplifier using general purpose op-amp. In the real field of application of instrumentation engineering, instrumentation amplifier always find its distinct position forever.